Hello everyone. So now let us look at the working and the simulation of an op-amp, following which we will try to build the layout for an op-amp. So in general, when you're building an op-amp, the blocks required are the differential amplifier and common source amplifier. So we have to remember that before we can commence the build for an op-amp, we require the designs of both the common source amplifier as well as the differential amplifier. And when we say designs, what we intend is that we have the schematic, the symbol, as well as the layout of both of them, that is the differential as well as the common source amplifier. Now let us again create a blank cell view first. So let me create a blank cell view and call it as op-amp, and I'm going to create a schematic for this cell view. So into this schematic we are going to call the existing differential and common source amplifier designs. So we have a symbol for a differential amplifier, and we have a common source amplifier as well. And let's look at what we have inside the differential amplifier. Let's do a descend on the differential amplifier. So this is the differential amplifier that we really are looking at, and this is the common source amplifier that we are working on. So let's go back, and now let's just connect them. And in order to complete the connections, we require pins here. So the pins are basically VDD and VSS, then a biasing pin, and the inputs, two inputs for an op-amp, and obviously the output. So let's create the pins themselves: VDD, VSS, IDC, V inverting, and V non-inverting. So VDD, VSS, IDC, V inverting, V non-inverting, and V output. Sorry, I didn't get a V output, so let's place an output pin called as V out, and let's do the wiring for the design now. So once we've actually completed the differential and common source, creating an op-amp would simply be interconnecting the two. Therefore it is very crucial that we have actually obtained the output correctly, the expected output for the differential as well as the common source amplifier, without which trying to continue with the op-amp would be futile. Now we have the op-amp completely connected, and once the op-amp is ready, I think we can go forward and create the symbol for the op-amp. So let me say create cell view from cell view, and let's create a symbol for the op-amp. So I'll keep the inverting and the non-inverting terminals only as the left pins. Let me make VDD a top pin and the VSS as a bottom pin, and the IDC also as a top pin. This is just a personal choice. It doesn't matter where the pins are placed, frankly, at this stage. So I prefer keeping it like this, and going ahead, this is the symbol that gets created. Now we do have the option of modifying this symbol and creating the symbol of an op-amp. I shall not go into that. I shall continue here and retain the same symbol. So now that we have the symbol, let's do a simulation of this. In order to do that, let's create a test bench waveform, and into this test bench I shall add the symbol that I just created. So I have the symbol, and along with this symbol I require the inputs for doing this test bench. So under analog lib, I think we should call in a sine wave, a sine voltage with an AC magnitude of 1 volt and an amplitude of 5 milli, or 5 micro would be better, because this op amp would probably give us an amplification of something around 1000 times. So the frequency would be 1 kilo, and let me give this to the inverting terminal. And for the source, to the power source, we require a DC supply. So let me call in a DC supply of DC voltage 2.5 volts, and let us give this as input to the VDC. We require another DC source of minus 2.5 as the source for the VSS terminal, and we would require a biasing current IDC of something around 30 micro. That's what we have designed this for, 30 micro. So let me keep a bias current of around 30 micro. And finally, I think we need ground, so let's bring in ground. This should give us ground, and with this I think yeah, one more, and finally we need the output pin. So let's call it Vout, and it's output already. So let me place that, and I think we are ready to do the wiring now. So the configuration that we are driving the op amp right now is one of an inverting amplifier. We are giving inputs only to the inverting terminal. The non-inverting terminal has been connected to ground, and we are giving an input in the microvolt range. And since the op amp has got a magnification and amplification of around 1000 times, I expect the output to be magnified, to be amplified somewhere in the millivolt range. I think our wiring is complete. Why don't we check? Yeah, it's done. The wiring is done. So now I think we can launch the test bench for this. So let me launch ADL, and let us do a transient analysis. So I picked a schematic where I have given the frequency as 1 kilo. So for 1 cycle would be 1 milli. So let me do a simulation for around 5 milliseconds, and let's add the DC analysis as well. Save DC operating point. Let's take the input as the DC source, and along with that, a start voltage of 0 and a stop voltage of 5 volts. That's very large. Let's keep the voltage lesser, significantly lesser. Let's say around 2 volts or 2.5, since that's the supply we are supplying, we are using here. And then an AC analysis of from somewhere around 10 to around 1 mega. I guess that should take care of the simulations that we require. And let's set the outputs where exactly we want the outputs from. We don't have any variables, so let's get the outputs. So the outputs are there in the input terminal and the output terminal. So let's look at the simulation now. Let's run this simulation. Let's check if it works. Yeah, it does. This would be very important for us. Let me put the layout as card, and let's look at the transient. So this is the input varying between 5 volts and minus 5 volts. So peak to peak the voltage will come to something around 10 microvolts, and the output is varying between something like minus 2.705 to around plus minus 2.11. So the difference is somewhere around 20 millivolts, 40 millivolts, right? So this comes to around 40 millivolts, and the input that we have given is 10 microvolts. So it is getting amplified by around 40,000 times. So the op-amp is working. It's working as an amplifier correctly. It's not biased well yet. It's not balanced, but it's working as an amplifier, and that is the primary objective of this experiment. So going ahead, I think the op-amp is working, and that should be sufficient for us. Let's go ahead and go into the layout of this op-amp now. So now that I have the differential and the common source, I require the layout for this. So let me launch the layout and ask it to create a new configuration for the layout. So let's generate the components. I think I already have the layout of the differential and the common source. Yeah, we do have these two already. So let me paste them, and so let's ask it to place it as in the schematic, and that should do it. So let's activate the connectivity now, and that should activate connectivity. So we have the input pins here, I guess. No, this is the VSS pin, this is the IDC. Oh, we haven't received the input pins. They're here, but they are not visible. Yeah, so these are the input pins and the output pin, VDD and VSS. Yeah, so we have everything that is required for the layout. So let's do a connection on these first. Right, so let me place the pins in close proximity to the design. That should eliminate most of your design related problems. So we can see that the VDD terminals are here, and there is an connection here. Now this connection is the tricky part in this layout here actually. So we have previously only used one metal when we wanted to make a connection. We've only used metal 1, but in this design metal 1 alone will not be sufficient because there are some paths that we have to cross over, and taking metal 1 over metal 1 will fail for us catastrophically. So what we really are going to do is we're going to place metal 1 to metal 2 wires, and in between these two we are going to pick the metal 2 wire, and we are going to do the wiring so that over this metal we have metal 2 wiring, but from here to the wire itself we are going to retain the metal 1 wiring. So this is pretty much clear on what we are actually doing here, and we have one more connection like that which are actually going to overlap. So let me finish the inputs again. So this should be the inverting and the non-inverting terminals, and this would be the IDC terminal. So let us just bring that about, and that should do it. So let me move the IDC pin slightly closer and wire this. Yeah, and the other pin that is of important to us is the VSS pin, and you can see that it is also going to overlap in this particular case. So I'm again going to put a wire. So let me put a wire here, and let's create a metal 1 to metal 2 wire for this place, and let's just take a metal 2 wire and connect it to this. This would be connected to the metal 1 wire, and let's complete this connection. So that's it. Yeah, let's take a metal 1 again and complete this wiring. So now we have no overlap in that particular region, and that shouldn't give us any problems as such. And finally we have the Vout pin. So let's bring the output pin onto this. So that's the Vout pin. So let me resize the entire thing slightly. It's unnecessarily huge. Okay. Yeah. So I think we are done with the layout here. Let's label them so that they are visible actually. So this is the inverting and this is the non-inverting terminal, and this would be the IDC, and this is the VSS pin, then this is the output pin, and this is the VDD pin. So yeah, all the pins are done, and this design is our differential amplifier and our common source amplifier. So this clearly is the layout of an op amp. Thank you everyone.